Beam me to the stars? That sounds like science fiction, yet a handful of bold researchers say it might soon become reality. Instead of hauling massive fuel tanks or exotic antimatter drives, they're proposing a radical new idea: using a high-speed beam of electrons to power spacecraft across interstellar distances. The payoff? Reaching the nearest star in decades rather than millennia, all thanks to a wild propulsion tech that bends the rules of space travel as we know it. This approach takes aim at a fundamental obstacle that has plagued interstellar dreams for decades: raw speed. Traveling to the closest star system, Alpha Centauri, is a 4.3 light-year trek. Our fastest probes, like Voyager 1, would take tens of thousands of years to get there. Even theoretical methods of speeding up a spacecraft, swinging by planets, diving near the sun, barely shave off a fraction of that time scale. To see results within a single human lifetime, you need velocities hovering around 10% of the speed of light. For reference, that's tens of thousands of kilometers per second. A rocket hauling any kind of chemical propellant quickly becomes impractical because the more fuel you carry, the heavier you are, which demands yet more fuel. It's a self-defeating spiral. Scientists have long known that one way around this is to beam energy to a spacecraft from an external source. Instead of dragging all your propellant and power on board, you receive it in real time from a station far away, letting you accelerate to speeds that ordinary rockets can't achieve. Proposals usually revolve around lasers pushing a sail or fueling a fusion ramjet. But those laser-based methods come with giant hurdles. Can you build a laser that powerful? How do you keep it perfectly aimed as your spacecraft zips away, possibly billions of kilometers from the origin point? Does the interstellar medium's low density hamper a ramjet's fuel intake? Enter the electron beam concept, championed in a paper by Jeff Greason, Chief Technologist of Electric Sky, Inc., and Chairman of the Tau Zero Foundation, and Garrett Bruhog, a physicist at Los Alamos National Laboratory. Their idea is to accelerate electrons to near-light speed, creating a long-range energy beam. A spacecraft riding in front of that beam could capture its momentum and power, channeling it into thrust. If done right, the craft could be propelled to significant fractions of light speed, covering multiple light years in mere decades. That might sound like science fiction, but it leans on existing physics. Particle accelerators on Earth already boost electrons to relativistic speeds, though only over short distances. The question is how to sustain a coherent electron beam across light years of vacuum. Because electrons all have the same negative electric charge, they repel each other. Normally, that would cause the beam to spread out and dilute, but in space, background plasma can come to the rescue. The interplanetary medium and beyond is full of charged particles, mostly protons and electrons from the solar wind or cosmic sources. When a tight bunch of relativistic electrons passes through that plasma, it pushes away the background electrons while leaving the heavier ions more or less in place. That mismatch creates a pinch effect, magnetically squeezing the electron beam so it stays focused. The faster the electrons move, the less time they have to disperse, which further stabilizes the beam. It's reminiscent of astrophysical jets from black holes or neutron stars. These jets can stay collimated over enormous distances because nature's version of a relativistic pinch effect is in play. The authors of the new paper propose replicating that phenomenon artificially. First, you'd position a powerful beam generator near the sun, where solar energy is abundant. Use solar power to run an accelerator that spits out electrons at nearly light speed, sending them streaming out along a specific direction. If everything's lined up, the beam remains narrow for billions of kilometers. A spacecraft traveling downrange in front of it receives this flood of electrons. The craft must convert the incoming electron energy into thrust, presumably by accelerating some onboard reaction mass outward. Essentially, you're still a rocket, but your energy is beamed from home rather than carried. The trick is ensuring the spacecraft doesn't melt. If you suddenly dump vast amounts of kinetic energy into a small probe, you need a highly efficient way to channel it into exhaust velocity instead of waste heat. The payoff, though, is enormous. According to calculations from Greason and Bruhag, you could push a 1,000 kilogram payload, roughly the mass of Voyager, 1 to 10% the speed of light in a few decades if the beam remains locked on. That means a journey to Alpha Centauri might take 40 years, long enough to feasibly see real data come back. They also suggest that electron beams, if done right, could be cheaper than massive laser arrays. Photons don't require focusing or worry about charge repulsion, but the power demands for a laser large enough to push a craft to interstellar speeds are mind-boggling. A single misalignment or minute diffraction effect can doom the mission. In contrast, electrons are easy to accelerate to high speeds, and once they're cruising in a stable pinch, they might remain coherent over stellar distances. That translates to needing less total power at the source, which cuts costs substantially. It also means you can push heavier payloads, not just gram-scale chips. Laser-based ideas such as breakthrough starshot usually talk about wafer-thin probes with minimal instrumentation. But the electron beam approach aims for something that can carry a full suite of sensors, power systems, and communications gear. Before you get too excited, major unknowns remain. One is whether the sun's magnetic field or other cosmic fields might disrupt the beam. Another is how you'd start the beam in the first place. The pinch effect might not kick in instantly. There must be enough background plasma and the right initial conditions. There's also the question of how the spacecraft stays within the beam's cross-section. Over decades of travel, any small deviation could mean drifting out of range. Guidance systems, or even multiple beam stations, might be needed to keep everything aligned. You then have the challenge of deceleration at the destination. If you want to stop at Alpha Centauri, you need an equal and opposite impulse. That either demands a second beam source on the far side, which we don't have yet, or a big chunk of onboard propellant to slow down. Failing that, you do a fast flyby, capturing glimpses of exoplanets and beaming data back. It's not perfect, but it might be the difference between taking 40 years versus 40,000 years. Even if interstellar missions are the ultimate prize, beamed electron propulsion could revolutionize nearer goals too. Within our solar system, you could transport cargo or humans much faster than conventional rockets allow, assuming you build the infrastructure. Place beam generators near Earth or the Sun to feed power to ships heading to Mars, the outer planets, or even deeper pockets of the Kuiper Belt. The same pinch effect might make it feasible to shoot a stable beam across the solar system. The big advantage is offloading your energy source to a platform that can harvest solar power near the Sun, where it's abundant. A smaller spin-off is power transmission. Instead of building giant solar panels on the Moon or shipping nuclear reactors, you could beam energy from the Sun's vicinity to remote installations. The same electron stream that drives a spacecraft could supply electricity for a base on, say, the lunar far side. Obviously, turning that raw electron flux into usable power is another engineering puzzle, but the principle is similar. If this works, we might build a cosmic network of electron highways, letting us shuffle cargo, people, and electricity around more flexibly. All of this remains, for now, on paper. The authors propose next steps. Run advanced simulations of how the beam interacts with plasma, see how the pinch forms, and confirm that it's robust. Then conduct small-scale experiments, perhaps in orbit, to see if a micro-scale electron beam can deliver stable thrust to a tiny test spacecraft. If those experiments match the models, you scale up. Ultimately, you'd try a real demonstration around the Moon, or deeper in the solar system. Only after success at that stage would we consider an interstellar attempt. It's reminiscent of other big ideas in advanced propulsion, from nuclear pulse drives to critics might question whether we can keep a space-based accelerator powered. You'd need enormous solar arrays or possibly orbital solar power stations near the Sun. Then there's the reliability factor. Can your hardware keep running for decades in the solar wind without failing? Could solar storms or flares disrupt the electron beam? The cosmic environment is unforgiving. A single glitch that misaligns the beam could doom your interstellar craft. If it works, though, the dream is seductive, launching probes that reach other stars in under a century, bringing back snapshots of alien worlds or scanning for biosignatures. If the exoplanet orbits a star only a few light years away, the round-trip communication time is manageable. 8 or 9 years for a round trip of signals with Alpha Centauri. That's far better than never. The difference between an 80-year mission and a 10,000-year mission is transformative. One remains within the realm of human planning. The other is effectively a forever project. The electron beam approach might also let us accelerate heavier craft than laser sails can manage. Laser-based proposals often talk about probes weighing just grams or at most kilograms. That imposes severe limitations on instrumentation, power, and communications. By contrast, if you can push 1,000 kilograms, you can haul a decent telescope, spectrometer, and robust transmitter. You could also include shielding to protect the craft from high-speed dust collisions, which become quite dangerous at 10% light speed. Naturally, it's not guaranteed that electrons are the perfect solution. Ion beams or even pulsed nuclear fusion might end up competing well. The novelty here is using space plasma to self-focus the electron beam over immense distances, drastically reducing power needs. That advantage alone could tilt the playing field if real-world tests back it up. Laser fans might reply that they can do similar focusing with advanced optics or gravitational lensing. The debate likely won't be settled until actual prototypes exist. One also wonders about the potential side effects. Will a continuous stream of relativistic electrons create a hazard for anything in its path? Are we basically firing a giant cosmic stun gun across the solar system? The paper hints that these details can be managed by carefully aiming the beam's path. Space is big, so the chance of accidentally frying, say, a passing satellite might be minimal. But it underscores the complexity of building giant energy infrastructures in a shared environment. In the near term, the authors talk about doing more computer modeling of how the beam starts and remains stable. That might involve simulating the sun's magnetic field lines and potential fluctuations from solar cycles. Then come smaller-scale tests, maybe a satellite in Earth orbit that tries to shoot an electron beam a few hundred kilometers, measuring how it stays focused. Another idea is to put a station at a Lagrange point that beams electrons to the moon. If that works, it'd be the first real-world proof of concept that electron pinch can be harnessed for space propulsion or power transfer. Step by step, we'd move from concept to practice. Even if electron beams never go fully interstellar, they could find a niche in faster solar system transport or high-power transmissions. Greason and Bruhag mention that beaming power over large distances is a game-changer for solar system infrastructure. Instead of building giant nuclear reactors on the Moon or Mars, you beam the needed juice from solar collectors in closer orbits. The difference from microwaves or lasers is that electrons, once accelerated and pinched, might cover huge distances without excessive spread, saving power. That alone might justify exploring the technology. For those who dream of star flight, each fresh idea offers a flicker of hope. Whether it's solar sails, laser sails, antimatter rockets, or electron beams, the question is always the same. Can we generate and deliver enough energy to cross interstellar gulfs in relevant timeframes? The electron beam concept says yes, if we exploit nature's own pinch effect. Of course, the gap between concept says yes and we've launched an interstellar probe is massive. But every big journey begins with a step, and perhaps a beam? One day, historians might look back and say, the electron pinch method unlocked the galaxy for us. Or it might remain a footnote overshadowed by some superior method we discover. Either way, the conversation about beamed propulsion is crucial. Chemical rockets, even nuclear thermal or nuclear electric designs, stall out far short of near-light speeds. If humanity aims to visit other stars, we must find ways to gather and project huge energy from a distance, circumventing the tyranny of the rocket equation. Electron beams are a fresh twist in that saga. No one's building an Alpha Centauri mission tomorrow. But if enough lab tests and orbital experiments confirm the viability of pinched electron streams, the path to starflight might open a crack. We could see a near-future demonstration that sends a small craft speeding around the solar system at unprecedented velocities. Then, maybe a larger follow-up that sets a new speed record for uncrewed vehicles. Eventually, when governments or private entities are ready to invest in the ultimate frontier, we'll have a blueprint. Beam me to the stars could shift from a pop culture catchphrase to a literal engineering plan. Skeptics remain, but that's healthy. Revolutionary concepts demand robust scrutiny. It might turn out that cosmic or solar magnetic fluctuations disrupt the beam more than expected, or that generating enough beam current is beyond our capacity. Then we'd refine or shelve the idea and try something else. But we won't know until we push forward. That's how space exploration has always advanced. From early rocketry to landing on the moon, it all started with what looked like wild leaps of faith. Whether electron beams ultimately succeed or not, they spark a conversation that keeps interstellar ambition alive. NASA, ESA, and other agencies focus primarily on local missions: Mars, Jupiter, Saturn. But there's no official roadmap for star missions because they seem too far off. Papers like Greason's and Bruhog's remind us that we have tools in our physics arsenal that might bridge that gap. If we harness them, the 21st century could lay the groundwork for a cosmic diaspora. Someday, a future generation might watch a real-time feed from a probe orbiting a planet around Alpha Centauri, and it all might trace back to the idea that you don't need your own rocket fuel if someone's willing to beam you power from behind. In the bigger scheme, electron beam propulsion underscores just how much we have yet to learn about harnessing energy in space. Plasma behavior, large-scale electric fields, advanced power beaming, these are frontiers of physics and engineering. Even if the full concept doesn't pan out for Starflight, partial spin-offs might transform how we do deep space missions. And that's worth investigating. The cost of ignoring potential breakthroughs is that we stay stuck exploring only the closest cosmic neighborhoods. If we want to become interstellar explorers, we need creative leaps. So will beaming electrons eventually replace rocket fuel for cosmic voyages? It's too early to say, but the potential is astonishing. If relativistic pinch phenomena in the plasma of space can guide an electron stream across billions of kilometers, then a small push from behind could accelerate a probe to speeds that truly boggle the mind. 40 years to Alpha Centauri might still sound long, but compared to tens of thousands of years, it's a revolution. That's the difference between an unattainable dream and something people alive now could witness, at least the start of it. One day, we might literally beam ourselves to the stars. In the meantime, the real journey starts with analysis, prototypes, and stepwise progress. If that's not the essence of humanity's spirit, taking big ideas and turning them into reality, nothing is. The upcoming years will show whether electron beams hold the missing piece to cosmic travel. If they do, well, maybe Star Trek's catchphrase, "Beam me up," was only slightly premature. The technology might be different from a transporter, but the result, covering impossible distances in feasible time, could be closer than we dare to hope.